Hi, welcome back. This is still Ken, and we're still in our course on mechanics, and this is the last stretch of our lesson on work and kinetic energy. In this video, we're going to discuss about your kinetic energy. The kinetic energy is the energy of a particle due to its motion, so anything that moves it has its kinetic energy. The kinetic energy of a particle is equal to your kinetic energy K, that is equal to 1/2 mv squared. K is the kinetic energy, m is the mass of a particle, and v is the speed of the particle. A change in kinetic energy is one possible result of doing work to transfer energy into a system. So to calculate for the work done for a system that moves, okay, consider for example here you have a block of mass m, and you are to apply a force F on the mass. For the mass to move to the right with an initial speed vi, so final speed vf. Now your block moves at some displacement delta x. So let us calculate for the work done. The work again is just equal to your fx dx, or your the sum of all your f dx. Okay. So here your F is just equal to the force that you apply, which is equal to your mass times your acceleration. But by the way, um, again your acceleration, this is equal to your change in velocity, rate of change of your velocity. So you have your dv over dt. Now if we're going to substitute this one to your equation, you have your work is equal to the integral of xi xf ma dx. So we substitute this one. You have your xi. No, sorry. I'm going to change this one already. So we have your m dv over dt dx. Okay, but your dx over dt is just equal to your velocity, right? So you have your velocity is equal to your the rate of change of your displacement x. So you have your m v dv. This time we change your integration, that is now from your initial velocity to your final velocity vf. So this is the work done for this moving block of mass m. Integrating this one, okay, so your mass is just a constant, so you can take it outside of the integration. So bif, and then you have vdv. So you just have your v squared over 2. So here you have your m v squared over 2, and we evaluate this one to from vi to vf. Okay, so that is why we have this one here. So you have 1/2 mvf squared minus 1/2 mvi squared. Now again, your kinetic energy is just equal to 1/2 mv squared. Okay, so this one here, this is your final kinetic energy minus your initial kinetic energy. So that means here that the total work done is just equal to the rate of change, or the change of your kinetic energy. So your net work is equal to your kf minus your ki, your final kinetic energy minus your initial kinetic energy, or you have your delta k. Now this equation here is what you call your work kinetic energy theorem. So the work kinetic energy theorem, or simply the work energy theorem, states that when work is done in a system and then the only change in the system is its speed, the net work done in the system equals the change in the kinetic energy of the system. So mathematically, your work energy theorem is just your work total is equal to your K2 minus K1, or your Kf minus Ki, or your delta K, your change in your kinetic energy. A 6 kg block initially at rest is pulled to the right along a horizontal frictionless surface by a constant horizontal force of 12 newtons. Find the block speed after it has moved 3 meters. Okay, so here we have a 6 kilogram block. Here this is the mass of your block. Initially at rest meaning you have your initial velocity, which is equal to 0, is pulled to the right along a horizontal frictionless surface by a constant force of 12 newtons. So you have some force F here. Find the block speed after it has moved 3 meters. So this is some displacement x, and our target here is the block speed after it has moved 3 meters. So that is your final velocity. From your work kinetic energy theorem, you have your work is equal to kf minus your ki. Okay, and since okay, so your work is equal to 1/2 mvf squared minus 1/2 mvi squared. Now this is just 0 here because your initial velocity is 0. So we can use this one to find for your your velocity f. Your work is just your force times your displacement s. So we have some displacement x or s. So you have 12 newtons times 3 meters. So this is equal to 36 joules. So you have 36 joules equal to 1/2 times the mass of 6 kilograms, and then your Vf squared. So you have 36 joules divided by 3 kilograms. You have Vf squared. Take the square root. So you have Vf, and this is equal to around 3.5 meters per second. So that is the speed of your block after it has moved 3 meters. Okay, from an initial from an initial 0 velocity. And we are finally down to our last topic, and this is about power. Power is the rate at which work is done. The average power PAV is equal to your delta W over delta T, and then the instantaneous power is equal to your dW over dt. The SI unit of power is the watt. Your 1 watt is equal to 1 joule per second. But other familiar units are the horsepower and then the kilowatt hour. You're familiar with the watt when you're going to buy your light bulbs. So it's in watts, like say for example 25 watts. Okay, you can use these conversions. 1 HP or 1 horsepower is equal to 746 watts or 0.746 kilowatts. So it's named from a horsepower because it was actually measured with your horses. Okay, so let's have an example. A 50-kilogram marathon runner runs up the stairs to the top of Chicago's 443-meter tall Willis Tower, the tallest building in the United States. To lift herself to the top in 15 minutes, what must her average power output in HP be? That is in horsepower. Okay, so your target is your power in horsepower. Your target is the power, the average power, PAB. Okay, so your power is equal to again your delta W over delta T. So we need to first find for your work done. Here you have your mass, 50 kilogram. And then here, this is the displacement. Okay, displacement, it needs to move up of your building. And then you have here some time, 15 minutes. Okay, so we need to find first for your work. So your work is equal to your Fs. Okay, so you have here your delta T. So your F is equal to your mass times your acceleration due to gravity times your displacement S over your time delta t. So you have your power is equal to um, you have 50 kilograms times 9.8 meters per second squared times your S. You have 443 meters, and then this is divided by 15 minutes, but your power is in joules per second, so you have 15 minutes, and then convert this one, you have 1 minute, you have 60 seconds. Okay, so using your calculators, let's calculate this one. Okay, so using your calculators, you get an average power equal to 241 watts, or in horsepower, this is equal to 0.323 horsepower. You just use your conversion of units on the previous slide. So that's it for this lesson. We've discussed so far about work, its definition in physics, and then we've described the work done by a spring, and then which is a classic example for the work done by a varying force. And then we've discussed the concept of kinetic energy and the work kinetic energy theorem. And then lastly here, we have discussed about your power. In the next lesson, we are going to discuss about your potential energy and then the energy conservation. So this is the end of lesson 6. On lesson 7, we're going to discuss about your potential energy and then the energy conservation theorem. See you in the next lesson. Thank you for listening.